So, collisions, momentum and kinetic energy. So rather than just looking at momentum being conserved, we're looking at whether kinetic energy is conserved or not. That leads us to two types of collision, and every collision can be classed as one of those two types. So momentum is always conserved, no matter what happens. Provided there's no external forces, then momentum will be conserved. Kinetic energy, however, is not always conserved. The first type of collision you can get is where momentum and kinetic energy are conserved. That's what we call an elastic collision. You can think of elastic as bouncing back to its original shape, so the amount goes back to what it originally was. There's nothing lost there at all. The second type of collision is an inelastic collision, and that's when the momentum is conserved, because momentum is always conserved, but kinetic energy is lost, or it's not conserved. It goes somewhere into another form of energy, for example. That's an inelastic collision. The most common type of collision is an inelastic collision. Most of the collisions that you encounter in everyday life or in the problems that you'll be asked within the exam will be inelastic collisions. So we looked at an example where one vehicle approaches another and collides, as is shown here. So it's different from the previous example that we looked at in that both vehicles are moving before the collision and both vehicles move off separately afterwards. So that's different from what we looked at before. But we still apply the same logic. We still draw in our masses in little boxes. We draw in our velocities of each individual mass before the collision. We draw an arrow to indicate when the collision has occurred, and after the collision we do the same thing. We draw those masses again with their new velocities. So we've got one missing velocity, and that's what we have to figure out. So we assume that momentum is conserved because there's no external forces here, so momentum is conserved. So all we do is calculate the total momentum of the objects before the collision and equate that to the total momentum of the objects after the collision. So this is M1, this is M2, this is U1, this is U2, this is M1, M2, V1 and V2. So we figure that out and we just work it through, solve for V, and we find that V was 10.7. So that's no different from the previous examples that we've looked at. The hardest part perhaps is remembering this equation here, but remember that all that is just an extension of P equals mv, which is the momentum of one object. All you're doing there is calculating the momentum of all objects and then adding the ones before the collision together and adding the ones after the collision together. The next thing we looked at, and this is the different part, is to show whether the collision is elastic or inelastic. This is a typical question to follow a standard sort of momentum problem, is to show whether the collision is elastic or inelastic. Now, whether a collision is one of those depends upon the kinetic energy. So we need to figure out kinetic energy before the collision, then kinetic energy after the collision as well. So I showed you two ways of doing that. We calculated the initial kinetic energy first. So we did the kinetic energy of object 1 before the collision, the kinetic energy of object 2 before the collision, then added them together and got a total there. After that, what you can do is do the same for final kinetic energy, figure out the kinetic energy after the collision of object 1, kinetic energy after the collision of object 2, add those together. And now you're comparing these two values, so you've got 118,000 and 117,094. So quite a big difference there. Kinetic energy is obviously lost, so you need to make a final statement there to say which type of collision it is. It's inelastic. It's inelastic because kinetic energy is not conserved. Kinetic energy is lost, not conserved, just means that some of it is gone missing somewhere. That's one way that you can do it. The second example I showed you, an alternative way of doing it, would be to do something similar to the conservation of momentum equation, and just do a half m1 u1 squared plus a half m2 u2 squared. So do all your calculations of kinetic energy before the collision together. So you're really kind of cutting your time in half. But that can be a wee bit more complicated, so that might not be something that you want to go for straight away, but it is there just to show you that there's another perhaps quicker way of doing it, just before and after. So we can do that, taking up half the space. And then just another statement there to say that EK after is less than EK before, so collision is inelastic. Your calculations on this type of stuff, it will be obvious. Someone asked yesterday, will it be clear that there is a difference between the kinetic energy before and the kinetic energy after? There will be an obvious difference. Either they'll be bang on the same, in which case the collision would be elastic, or there will be an obvious difference between the two. in which case it's inelastic.